If you want to build an artificial intelligence that can safely drive a car, the worst possible thing you can do is show it 50,000 hours of perfect sunny highway driving.
Right, which sounds completely backwards when you first hear it.
It does. But, feeding a model massive amounts of flawless data is exactly what causes it to fail when it finally encounters the real world. Welcome to TalkKast. Just the other day we were talking about how Anthropic's new AI could affect all of us, focusing mostly on the big societal ripples.
Yeah, the economic shifts, the cultural impact, all of that.
Exactly. But there's this massive gap between acknowledging the power of these models and actually understanding, the physical and mathematical reality of how they're built in the first place.
Oh, absolutely. I mean, if you ask most people to picture modern AI being created, they imagine, endless rows of unimaginably powerful supercomputers in some windowless data center.
Right. Just furiously crunching the entire internet to build an omniscient digital brain entirely from scratch.
Exactly. But the reality of the industry right now, like the actual work happening on a random Tuesday morning at an AI startup, it looks profoundly different.
It's a huge misconception, isn't it?
It really is, and it completely skews our perception of what artificial intelligence actually is today. The idea of building a massive digital brain from absolute zero, what the industry calls pre-training, is an endeavor reserved for maybe half a dozen companies on Earth.
So when we hear about those billion-dollar compute budgets and server farms packed with tens of thousands of GPUs, that's just the pre-training phase.
Precisely. That phase is simply about teaching a system the fundamental statistical representations of reality.
Okay, so just feeding it unstructured petabytes of text.
Yeah, so it can build an internal map of human language, logic, and basic reasoning. But for the rest of the technology sector, building an AI product is not about building from scratch at all.
So what are they actually doing?
It's entirely about taking an existing, highly generalized model and steering it. You take a system that already understands the geometry of the world and rigorously constrain it so that it performs one highly specific task flawlessly.
I really want to break down that concept of steering because it fundamentally changes the barrier to entry for this technology. If most engineers aren't building these foundational brains, what does the architecture of training actually look like?
Well, you have to look at modern AI development as a three-tiered architecture. The first tier is the pre-training we just mentioned, which outputs a base model.
And a base model is essentially just a hyper-advanced autocomplete engine. Right?
Exactly. If you ask a raw base model a question, it might answer it, or it might just generate a list of similar questions. It's only predicting the most statistically likely next word.
Because it's just trained on raw internet data.
Right. To make it actually useful, you have to move to the second tier, which is supervised fine-tuning, or SFT. This is where 99% of production teams live.
Okay, so what exactly happens in SFT?
In SFT, you take that generalized model and you physically alter its internal weights by showing it highly curated, formatted examples of exactly what you want it to do.
So you provide an instruction and then provide the perfect response.
Yes. You are narrowing its probability distribution. And then the third tier is preference alignment. This is where you shape the behavioral boundaries like safety, tone, and refusal mechanics.
Let me test a mental model here. If pre-training is putting a model through 20 years of general education so it understands math and history.
Right, a general understanding of the world.
Yeah. Then supervised fine-tuning is hiring that college graduate and handing them an employee handbook. You're saying, you already know how to write, but here is the exact template we use for invoices at this company.
That captures the intent perfectly.
And then preference alignment is the manager pulling them aside to say, hey, when you send those invoices, use a polite tone and never use profanity.
That's a spot-on analogy. But mathematically, what is happening in the network during that preference alignment phase is what really catalyzed the current boom. For a long time, we relied on a technique called RLHF.
Reinforcement learning from human feedback.
Exactly. And RLHF was incredibly complex. It required you to train a separate reward model that acted as a judge, and then use highly unstable reinforcement learning algorithms to update the main model.
That sounds like you're trying to balance multiple massive neural networks all at once.
You are. It required enormous compute power and a team of PhDs to keep it from collapsing. But recently, the industry shifted toward a technique called direct preference optimization, or DPO.
Okay, so how does DPO do that? If you don't have a reward model judging the answers, how does the AI know what you prefer?
The researchers who developed DPO found a mathematical shortcut. They realized you could express the human preference directly within the language model's own loss function.
Wait, really? So instead of building a complex reward system,
You just show the model two answers, one you like and one you reject. The DPO algorithm calculates the probability of both answers and directly updates the model's weights.
oh wow, so it increases the likelihood of the chosen response while heavily penalizing the rejected one.
Exactly. It bakes the preference directly into the core math of the model.
And because you bypass that entire secondary reward model, you drastically reduce the hardware requirements.
You do. And that pairs perfectly with another critical technique called LoRa, which stands for low-rank adaptation.
I've heard of LoRa. How does that fit in?
Think about a massive model with 70 billion parameters. Fine-tuning it traditionally means you have to load all 70 billion parameters into active memory, calculate the gradients, and update every single number.
Which sounds like a staggering amount of memory.
It is. But LoRa uses a brilliant piece of linear algebra. It freezes the massive original model completely. It doesn't touch those 70 billion parameters at all.
Wait, then how does it learn anything new?
Instead, it injects two tiny low-rank matrices alongside the frozen layers, and you only train those tiny matrices.
Oh, I get it. So instead of trying to remodel the entire skyscraper, you're basically just swapping out the lock on the front door.
Precisely. You're only updating a few million parameters instead of billions. When the model generates text, it combines the knowledge from its frozen base with the specific instructions learned in the tiny LoRa adapter.
That's incredibly efficient.
Because of DPO and LoRa, fine-tuning a massive large language model no longer requires a $20 million supercomputer. You can execute a fine-tuning run in a matter of hours on a single consumer-grade GPU.
Like the exact same graphics card someone might have in a high-end gaming PC at home.
Literally the exact same card.
But wait, this introduces a massive contradiction.
How so?
Well, if the foundation models are openly available, and the techniques to steer them, like LoRa and DPO, run on hardware you can buy off the shelf, why isn't every single company on Earth deploying flawless AI? I mean, the barrier to entry has mathematically evaporated. So why do we still see these systems constantly hallucinating, failing at basic data extraction, or acting unpredictably? What is the actual bottleneck?
The bottleneck is the dirty secret of modern machine learning. The absolute ceiling on what your model can accomplish is no longer the compute budget, and it's no longer the elegance of the algorithm. The bottleneck is entirely the data.
The data. But I thought the whole point of AI was feeding it as much data as humanly possible.
The industry is undergoing a massive paradigm shift regarding data quality right now. For a decade, the ethos of the big data era was sheer volume. The assumption was that if you fed a neural network enough data, it would eventually find the hidden patterns, regardless of how messy that data was.
And that's not true anymore.
We are now realizing that during the supervised fine-tuning phase, volume is actually your enemy.
Wait, really? Why would volume be the enemy? If the model needs to understand every possible edge case, shouldn't you give it as much information as possible?
Because fine-tuning is not about teaching the model new facts, it's about defining a highly specific behavioral manifold. You're teaching the model exactly how to format its output and how to reason through a specific type of problem.
Oh, I see.
If you fine-tune a model on 50,000 scraped, mediocre examples, you are inevitably introducing noise. You introduce formatting errors, contradictory logic, lazy reasoning, and the model internalizes all of that.
It just absorbs the bad habits.
Exactly. It's mathematically much harder for a neural network to unlearn a bad habit than it is to learn a precise rule from a pristine data set. A model fine-tuned on just 500 perfectly curated, highly verified examples will vastly outperform a model trained on 50,000 noisy ones.
It's like the difference between learning to play piano from a master instructor for 10 hours versus spending 1,000 hours listening to an amateur bang on the keys.
Yes.
You're just going to build muscle memory for the mistakes.
Yeah.
But how does that failure actually manifest in the technology? What does it look like internally when a model is trained on the wrong kind of data?
The most dangerous manifestation is a phenomenon called class imbalance. Think back to the autonomous vehicle example you mentioned at the start.
Right, the sunny highway driving.
Exactly. When an engineering team sets out to train the vision model for a self-driving car, they pull data from their test fleet. Naturally, the vast majority of driving occurs in relatively good weather on well-marked roads.
Sure.
So the data set becomes overwhelmingly dominated by clear, sunny highways. The AI processes millions of frames of a stop sign on a bright day. But out of those millions of frames, perhaps only 2 or 3 show a snowy road with a faded stop sign partially obscured by a branch.
And from a statistical standpoint, the neural network probably looks at those 2 snowy images and decides they're essentially a rounding error.
Exactly. They are mathematically insignificant compared to the millions of sunny images. The neural network optimizes its internal weights to minimize loss across the entire data set. The gradients pull aggressively toward the features of a sunny day.
So the snowy stop sign just gets ignored.
The unique visual features of the snowy stop sign get mathematically washed out in the batch averages. When that vehicle is deployed into the real world and encounters a blizzard, the activation functions in the neural network simply do not trigger. It fails. And it doesn't fail because the convolutional neural network is poorly designed. It fails because the probability distribution of the training data did not match the real world. Google research actually found that these specific data quality issues are pervasive across the industry.
And I imagine they cause cascading failures that go completely undetected until the model is almost deployed.
Exactly.
That makes perfect sense, but it also sounds like a paradox. You need perfect data, but the real world isn't perfect. I want to bring up a real-world example that perfectly illustrates this tension.
The ComFox case.
Yes. The story about Chris Lyle, the co-founder of ComFox. His team was building an AI designed to search and extract information from complex legal and financial documents. Like any logical engineering team, they initially curated a pristine dataset, perfectly clean, beautifully formatted digital text. But when they deployed it to their users, the system's performance completely cratered.
And do you know why?
Because the real-world users weren't searching through pristine digital text. They were uploading messy, scanned PDFs filled with optical character recognition errors, weird line breaks, and, coffee stains.
This perfectly highlights the vulnerability of tokenization in large language models. When an AI reads text, it doesn't see letters the way we do. It uses a tokenizer to break words into subword chunks and assigns each chunk a specific integer ID.
Right, and those IDs are mapped to a high-dimensional vector space.
Exactly. Let's say a clean document has the word return. The tokenizer processes that perfectly. But in a messy scanned PDF, an OCR error might merge the letters R and N together, interpreting them as an M, so the word becomes retum.
And to the AI, retum isn't just a slight misspelling. It completely changes the tokenization.
Completely. The model assigns it a completely different integer ID, which corresponds to a completely different sector of that vector space. The mathematical relationship to the surrounding words is destroyed.
Because the self-attention mechanism, which determines how much focus a word should have, suddenly sees a garbage vector.
Precisely. The entire mathematical structure of the sentence collapses. ComFox realized their pristine data was actually a liability because it didn't reflect the true distribution of their users' environment.
So what did they do?
They completely reversed their strategy. They took their perfectly clean training data and intentionally poisoned it.
They intentionally dirtied the data set.
Yes, they wrote scripts to introduce simulated OCR errors, artificial formatting glitches, and the exact kind of messy noise their users were generating.
And the results were fascinating. When they tested the new model in a perfectly clean environment, the raw accuracy actually dropped by about 8%. But its real-world relevance, how well it actually solved the user's problem, jumped a massive 34%.
It's a brilliant example of data augmentation. By introducing that specific targeted noise, they forced the model to learn more robust representations. They forced it to map those noisy tokens back to the correct semantic space.
So preparing this data sounds incredibly tedious and precise. It's not about laboratory perfection, it's about matching reality.
It requires meticulous domain-appropriate annotation that heavily indexes on the messy edge cases. You cannot outsource this to cheap, generalist crowd workers. Data preparation now consumes 20 to 30% of the entire budget for modern AI projects.
Which brings us to the actual execution. If you have an engineering team sitting down to build an AI product, and they know data is the bottleneck, how do they actually navigate this? What is the concrete workflow to get from raw, messy data to a functional AI?
Well, there is a highly structured 6-step blueprint that almost all series production teams follow today. And the critical thing to understand is that the first step involves absolutely no coding.
Okay, what's step one?
Step one is defining the problem mathematically. You have to establish rigorous, measurable success criteria.
So you can't just say, let's make our search feature better.
Vague goals lead to endless, expensive iteration. You have to define what better actually means. Are you optimizing for accuracy? What is your latency budget? If the model is 99% accurate but takes 12 seconds to respond, is that a failure?
Specificity creates a mathematical finish line. It sounds exactly like building a house. You don't hand a contractor a blank check and say, build me a good house.
Right.
You provide architectural blueprints detailing the exact square footage, the load-bearing tolerances, the material specs. Without that, you just iterate until you run out of money.
Exactly. Step 2 is the data pipeline. As we established, this is the make or break phase. You collect your data, and then you build a rigorous annotation pipeline.
And this is where you need domain experts, right?
Yes. This isn't just about labeling. You need protocols to measure inter-rater reliability, which mathematically calculates how often two different human experts agree on a specific label. If human experts can agree on how to label a complex financial clause, the neural network has absolutely no chance of learning it.
Ambiguity is the enemy. So the foundation is poured, we have a mathematically defined goal, and an unambiguous data set. What's step 3?
Step 3 is choosing your framework and your starting model. The golden rule here is to start with the smallest possible pre-trained model that fits your hardware constraints and scale up only if your metrics prove the small model lacks capacity.
What about the software ecosystem?
Right now, PyTorch is the undisputed sovereign of the AI ecosystem. It's used heavily with tools like Hugging Face. Its dynamic computation graph allows researchers to execute and debug code immediately, making it incredibly flexible.
You hear a lot about TensorFlow and Google's JAX. Where do they fit into the landscape?
They serve highly specific niches now. TensorFlow is relegated mostly to edge and mobile deployment because of its static computation graphs. And JAX is a phenomenal mathematical framework, but it's mainly for Google's massive TPU pods. It requires deep engineering expertise.
So for the vast majority of teams, PyTorch is the default. Okay, we have our blueprint, our data, our framework. Step 4 is where we configure the training, right?
Yes, step 4 is configuring the training dynamics, which centers heavily around hyperparameter tuning.
How are hyperparameters different from regular parameters?
Regular parameters are the knowledge the model actually learns during training, the literal weights connecting the artificial neurons. Hyperparameters are the external settings you configure before you ever press start. They dictate exactly how the model updates its internal knowledge.
And the learning rate is the most impactful one.
By far. It controls the magnitude of the mathematical steps the model takes when it updates its weights in response to an error.
It sounds like learning rate is exactly like driving on a new, unmapped road.
How so?
Well, if you drive too fast. If the learning rate is too high, you blow right past your destination. You realize you made a mistake, jerk the steering wheel, and overcorrect. But if you drive too slow, you run out of gas before you ever get there.
That analogy captures the risk perfectly. Physically, it's like navigating a foggy, incredibly high-dimensional valley using gradient descent.
You're trying to find the bottom of the valley.
Yes, the bottom of the deepest valley is your optimal solution, where the model makes the fewest errors. If your step size is too large, you might literally step entirely over the deepest part of the valley and bounce up the other side.
But if it's too small, you get trapped in a shallow valley.
Exactly. So teams spend immense amounts of time engineering learning rate schedulers to zero in on the optimal solution.
Okay, so we've calibrated our step size. We initiate the training run. What is happening in step 5?
Step 5 is training, monitoring, and aggressively preventing overfitting. You do not just hit execute and go get coffee. Engineers use tools like weights and biases or MLflow to watch real-time loss curves.
They're watching the training loss versus the validation loss, right?
Exactly. Training loss shows how well it's learning the data it's looking at, and validation loss tests it on a separate dataset it has never seen before. If those two curves diverge, if performance on the unseen data gets worse, it means the model has stopped learning logic and started purely memorizing the training data.
It's like a student who memorizes the answers to a practice test, but fails the actual exam because they didn't learn the concepts.
Precisely. When engineers see that, they use techniques like early stopping to halt the training. It requires multiple iterations.
Which finally brings us to the real world. Step 6. The model is trained, it generalizes well, and we deploy it. Is the work done?
The development phase is done, but the operational phase is just beginning. Step 6 is deployment and continuous monitoring. And the primary threat here is an insidious phenomenon known as concept drift.
Concept drift, what does that mean?
The real world is not static. Over time, the probability distributions of the data your model encounters in the wild will inevitably shift away from the data you use during training.
Can you give me an example of what that drift looks like in practice?
Sure. Let's look at concept shift. where the average relationship between the input and the output changes. If you trained an AI in 2019 to extract data about average home prices, the underlying economic reality of what constitutes an average price has shifted drastically today.
Oh, wow. So the model's logic is fundamentally outdated.
Right. And the danger of concept drift is that the model doesn't crash. It doesn't throw an error code. Its performance just silently, gradually decays. You have to build robust pipelines to detect this mathematically and trigger automated retraining.
That is fascinating. The AI itself doesn't degrade. The world just moves out from underneath it.
Exactly.
This 6-step blueprint, defining the problem, curating data, selecting PyTorch, tuning the learning rate, monitoring loss, and defending against drift, makes complete sense abstractly. But AI isn't just one thing. Does this process change if we are teaching an AI to read a contract versus teaching it to see the road or speak with a voice?
The foundational rules apply across all those different senses. But the failure points, the specific bottlenecks, change drastically depending on the modality.
Okay, let's do a deep dive into those modalities. Let's look at text first.
Right. Natural language processing. Models like Lemma 4, Qwen 3, or Gemma 3 rule text generation right now. When you're fine-tuning these, the focus is almost entirely on consistent formatting and structural priors.
What do you mean by structural priors?
Teaching the model the specific template of how it should output its internal knowledge. Let me give you a real-world success story. A company called Guardrails AI needed to build a highly accurate open-source validator to detect hallucinations in financial documents.
Based on the old big data paradigm, you'd assume they needed to scrape millions of financial PDFs.
They didn't. They had a team meticulously curate and label exactly 1,000 sentences.
Wait, really? Just 1,000 sentences?
That's it. But from those 1,000 sentences, human experts carefully extracted over 5,000 highly specific factual claims, formatting the extractions flawlessly. It took roughly 3.5 weeks of highly skilled human labor.
So it wasn't about volume. It was the density of the relationships within the text.
Precisely. Because the dataset was so factually dense and the formatting so rigid, that tiny dataset was enough. It learned the exact structural prior necessary. 1,000 perfect sentences built an enterprise-grade hallucination validator.
It completely shatters the illusion that fine-tuning requires limitless data. Okay, so for text, success hinges on factual density and strict formatting. But teaching a computer to see the world feels mathematically much heavier. How do the failure modes change for vision?
Vision is undergoing a fascinating architectural split right now. If you're building a system that needs to run inference locally on a small device, you're still primarily using convolutional neural networks or CNNs.
But what about real-time object detection, like for a delivery drone or a self-driving car?
For that, the YOLO series is the undisputed standard YOLO 11 and YOLO 26. YOLO stands for You Only Look Once. It predicts multiple bounding boxes and class probabilities across the entire image in a single pass, which makes it incredibly fast.
And what if you need the AI to understand massive, complex visual contexts, like huge data sets?
Then you move to Vision Transformers, or VIT. Instead of sliding a filter over an image, VIT chops the image up into a grid of distinct patches and processes them using the exact same self-attention mechanisms that text models use.
Oh, I see.
But regardless of the architecture, the absolute critical failure point in Vision AI is the geometry of the annotation.
The geometry of the annotation, you mean how the human labeler actually draws the shape around the object in the training data?
Exactly. Historically, we use bounding boxes. You just draw a simple rectangle around the car or the pedestrian. But bounding boxes have a severe geometric flaw. Imagine drawing a rectangle around a car that is parked diagonally.
The car only fills maybe 50% of that rectangle. The other 50% is background like asphalt or shadows.
And the neural network is completely agnostic to what the object actually is. It just looks at the pixels inside the box. So it inevitably learns that the texture of the asphalt is part of the mathematical definition of a car.
So it learns the background features. That has to cause massive failures when objects overlap.
It does. To solve this, advanced teams use polygon masks. A human annotator traces the exact pixel-perfect outline of the object, completely isolating it from the background.
Like the company Nodar, right? I read they needed 60,000 precise polygon masks to properly train their depth mapping models for cars and agriculture.
Yes, 60,000 hand-drawn, pixel-perfect masks.
That is an astonishing amount of meticulous human labor. An engineer sat there and individually traced the tread of a tractor tire thousands of times. But I imagine that eliminates the background noise entirely.
It does. The model learns the true visual features of the vehicle. The precision of the human hand directly dictates the safety of the autonomous system.
So text requires structural formatting, and vision requires pixel-perfect geometric isolation. What about voice? We interact with voice AI constantly. What's the bottleneck for teaching an AI to listen?
Voice is perhaps the most revealing modality. We use incredibly powerful models like OpenAI's Whisper or NVIDIA's Parakeet. But the critical insight is this. When a voice model fails in production, it is almost never an architecture problem.
What is it then?
It is virtually always a data coverage problem. It fails because it encountered something the data pipeline missed, like missing regional accents, compression artifacts, or background wind noise.
But I've heard the most bizarre failure mode in voice AI is the hallucination of complete sentences during dead silence.
Yes, it's autoregressive decoding. The language model powering the transcription is mathematically desperate to predict the next token.
Wait, so the AI will invent words when nobody is speaking just to fill the void?
Exactly. If the training data did not include sufficient examples of dead silence properly labeled as no speech, the model doesn't know how to handle the absence of an acoustic signal. It relies entirely on the structural priors it learns during pre-training.
So it grasps at the static.
And it hallucinates a phrase, often something strange like, "thanks for watching," simply because a massive portion of its pre-training data came from YouTube transcripts where silence often preceded that exact phrase.
That is incredible. It hallucinates a YouTube sign-off because human beings forgot to mathematically define what silence looks like.
Exactly.
Okay, there is one final modality we have to explore. AI image generation. When we are training systems like Stable Diffusion, how do we steer them?
Image generation relies on latent diffusion models. When a team wants to teach an image generator a specific new concept, they generally choose between 3 techniques.
What's the heaviest option?
Dream Booth. It involves unfreezing the UNet and directly updating its core weights. It provides the absolute highest fidelity, but the resulting file is massive, and it suffers from language drift, where the model forgets how to draw other concepts.
It's like buying a massive, custom-built canvas just to show someone a sketch. It's heavy and inflexible. What's the alternative?
The production standard is LoRa, which we discussed earlier. It freezes the main model and injects low-rank matrices, keeping the file size tiny. It's entirely modular. The third and lightest option is textual inversion.
How small does that get?
Microscopic, usually around 12 kilobytes. It doesn't touch the visual model at all. It just searches the text encoder to find a brand new, unique vector that describes your images.
So regardless of which technique you use, what is the bottleneck here? What causes these image models to fail?
The absolute biggest secret in fine-tuning image generators has nothing to do with the resolution of the images. It is entirely dependent on the caption accuracy.
Caption accuracy.
The model only learns to associate visual features with the specific words you explicitly include in the caption. Let's say you want to teach the model a specific sports car, and you upload 10 photos, but in every photo, the car is parked on grass.
Right.
If your caption simply reads, "a photo of the sports car," the neural network analyzes the pixels and realizes that the green glass is consistently present. It mathematically binds the grass to the concept of the car.
So if you ask it to generate the car on a city street,
It will generate the car, but the street will be made of grass. The model didn't fail. It perfectly learned the flawed logic you presented. You have to explicitly caption the grass so the model learns to separate the background from the subject.
listening to this breakdown across all these different modalities, a profound pattern really emerges.
It does.
Whether we're looking at a language model failing to extract a fact, a YOLO vision system misinterpreting a snowy intersection, a whisper transcription model hallucinating a YouTube sign-off in an empty room, or a diffusion model drawing a street made of grass. In every single one of these scenarios, the AI doesn't fail because the math is broken. It fails because human beings didn't label the data correctly. We didn't draw a tight enough polygon, or we forgot to include an accent, or we wrote a bad caption.
That is the inescapable physical reality of the technology today. We become so captivated by the algorithmic magic that we completely ignore the human labor required to shape it.
We're rushing toward automation, but the models themselves are proving that highly specific, incredibly accurate human context is the most valuable currency left.
Absolutely. The models are powerful engines, but the fuel is human knowledge, carefully distilled and verified.
It really is a profound irony. We tend to think of artificial intelligence as this cold, mathematical, almost alien technology. Yet the absolute limit on how smart an AI can get is entirely dependent on the meticulous, deeply human labor of data annotation.
We are literally teaching these systems by hand.
One carefully drawn polygon or one perfectly transcribed audio clip at a time. Next time you see an AI generate something absolutely flawless, take a moment to ask yourself, whose hands shaped the data that made that mathematical miracle possible? Thanks for listening to TalkKast.